Why don't, yeah, you should go first. So, I mean, you don't have much of an option. Yeah, exactly. So we're going to do Faye is going to split, and she's going to then move these chips apart. I think that is a great move. So I think I will also be splitting on my turn. So I'll split here at the 0 index, and now it's Faye's turn again.
And I'll combine.
Okay,
I'll combine the 0 and the 1.
Yeah, so here it is highlighted in orange, and then the combine move plays out. I think I will also combine. So I'll take the indices here at the 1 and the 1, and I'll combine them over onto the 3rd index. And now it's your turn again.
And I'll split.
So splitting over there on the left, we can see what happens. And now it's my turn. I will combine, so taking the -1 and the 0 indices. So you can kind of get an idea of how these moves play out. But now it's your turn again, Faye.
I combine.
Right, taking those orange ones. We're getting towards the end. It's my turn. I think I'll combine also over here on the right. And now it's your turn.
And I split, and I win.
Darn! Yeah, I can't make any more moves. So Faye is the winner of this. But I lose. But as we'll see, even when you lose, you can gain something. You can learn from your defeat. So what the lesson that we'll learn, we'll see once we get through this slide. So the polynomial x squared minus x minus 1, you may recognize it has the golden mean as one of its roots. It works well with the two moves that we've designed, namely because x squared equals 1 plus x. You can see it's just very basic algebraic manipulation to get that. And also 2x squared equals 1x plus x cubed. These two equations really represent the moves that we're doing. So on the left, x squared equals 1 plus x. You can think of that as saying, if I have, so you look at these exponents as denoting the number of chips at an index. So the exponent of 2 means that we're at the second, or that we have 2 chips at some index. And it's saying, okay, you take these 2 chips, you take a chip at the 0 index, so 1 is x to the 0, and a chip at the first index, x to the 1, and you can have those be equal to x squared. And the same idea with the equation to the right. 2x squared is saying that we have 2 chips at an index, and now we can take one of them, move it over to the one index over, and the other one 2 indices to the left, and we still have the same amount. So when we have x as the golden mean, these values are actually going to be preserved. So as we play out the game, the quantity that we started with actually remains the same because these moves don't change the total value. So what we actually did when playing this game was that we started out with a 9 in the 0 place, so phi to the 0 times 9. Well, that's just a 9. And as we played out this game, we kept the same value, and we ended up with a representation of the number 9 in base phi, and so an irrational base. That's surprising. But moreover, we actually ended up with a representation as a sum of non-consecutive powers of phi, because it's going to be a string of 1s and 0s, and there's never going to be any 2 ones adjacent to each other. And just as an FYI, the name Bergman comes from George Bergman, who was the one who found out that you could represent any integer as a sum of powers of phi, and then we call it the Bergman game because the game really does is it generates this sort of decomposition. So these moves seem kind of out of nowhere, the setup. So how did we come up with this? Well, the Fibonacci numbers, as you may be familiar with, are this recursively defined sequence starting with initial values 0 and 1, where the next value is defined as the sum of the 2 prior ones. And a result by Zekendorf is actually that every positive integer, no matter which one, can be uniquely written as a sum of non-adjacent Fibonacci numbers. Sounds familiar, right? We were just talking about base phi, sum of non-adjacent values. But here it is for the Fibonacci numbers. So for example, 2021, that's a positive integer. We can write it as this sum of Fibonacci numbers, 1597, which is the 15th Fibonacci number, 377, which is the 12th, 34 is the 7th, and 13, which is the 5th. And it ends up being the value. And this arises for any positive integer we choose. And there's this thing called the Zekendorf game, which is very familiar, very similar to the Bergman game, which we just played, except that it's instead of a doubly infinite tape, it's just a one-way infinite tape, because right, the indices of the Fibonacci numbers, there's no negatives there. It's just all like 0, 1, 2, 3, 4, 5, and so on. And the game and the rules for this Zekendorf game are slightly altered. We won't get into that because there's just like boundary conditions that are slightly different. But anyway, similar to the Bergman game, when we play the Zekendorf game, what we end up producing as the final game state is a Zekendorf decomposition, which again is this unique sum of non-adjacent Fibonacci numbers. And we can kind of compare these two games a little bit. So on the left here, we have a sort of representation of a Zekendorf game where the setup is kind of similar to the game that we played, where every row represents a game state. So you can think of it as like marching down from the top to the bottom. And wherever we have a non-zero number of chips at an index, we color it in with a black square. So you can just keep track of where there's actual like numbers occurring. And then both of these games are starting out with 20 chips at the 0 index. And on the right, there's the same 20 chip game, but now using the rules of the Bergman game. And you can see how it's a bit more complicated given how much we had to zoom out of the picture to fit both of these games onto the same slide. And even though it is much more complicated, there are things we can study about it, results we can find, some invariants we can define, and to talk about those now is Faye.
Thank you, Luke. So we know a lot about the Zekendorf game. We know how quickly it terminates. We even know who wins. It turns out the second player wins, but the proof is non-constructive. So we want to try and figure out similar things about the Bergman game. So the first thing to approach is termination. It would be really bad if we were playing a game and it would never end. So we hope it terminates. How are we going to prove that? So to do that, we're going to use invariants and monovariants, which is a common technique. So the natural invariant to consider is what we'll call the value. And this is just taking the base phi decomposition and taking it to heart and defining the value of a game state as the sum of the powers. And it's an invariant basically just because the polynomial works well with the rules. It's kind of designed that way. So there's no tricks up my sleeve. So as you can see here, we play the game and we always have a value of 9. So we can go to the next slide. There's another monovariant, which is very useful, which is the number of chips. And this is useful because we can look at it and whenever we split, we're just moving chips around. So we're not going to change the number of chips. But whenever we combine, the number of chips is going to go down, which means the number of combines is bounded by the number of chips we start with. This is great because it means that to prove that the game terminates, all we have to do is bound the number of successive splits, which you can kind of think about on your own. And so we can go on. And to bound the number of successive splits, we need a new monovariant, which is much worse. In fact, it's not even monovariant under combines. So this is called the index sum. And what it does is it just takes instead of taking the number of chips at an index and multiplying it by the power of phi, you just multiply it by the actual index. And when you do that, you get this awful expression that kind of doesn't represent anything. But thankfully, a split decreases this value by 1. And so that allows us to bound the number of successive splits, as long as we can bound the index sum above and below, which we'll do in a second. And then a combine into index j just increases this by negative j plus 3. It's a little bit wonky. Okay, so here's the general strategy of how we prove termination. So we need bounds on either side of the game state in order to understand the index sum and be able to bound that. So there's a very easy right bound, which is log base phi of the initial value, or really the value through any point in the game because it stays the same. And this just comes because phi to any power is positive, and you can take log base phi of the value. That's the farthest right you can go, because if you had a chip there, you would be really big. So that tells us how far to the right we can go. And we can actually use how far to the right we can go to figure out how far to the left we can go. And the way you do this is you take the maximum gap size between summands. So this is like the longest run of zeros that ever occurs in the game. And you can bound that, namely because a combine is the only thing that can make that bigger, if you think about it for a little bit. And then because the combine is the only thing that can make that bigger, up to a little bit of fudging, that means that because we know how many combines there are, we can figure out the maximum gap size. Then you go to the right bound and start placing chips. Place one at the right bound, maximum gap, place one, place one, place one, and that tells you a left bound. This is a really bad worst case analysis, and you'll see why in just a second. But it does give us a maximum and a minimum for the index sum. So proposition, the Bergman game actually terminates. This is great. So you have this many combines, and we just need to bound the number of successive splits. And we know that a split decreases the index sum by 1, but the index sum is bounded below. And so we're done. It's bounded below because you have right and left bounds. Okay. So this termination time is hiding something. Namely, the left bound is really, really, really awful. And so the termination is exponential. And if you want to think about this as kind of a algorithm for producing these base P decompositions, it's a really nice algorithm because it's precise. You will never make mistakes by floating point errors because you can just view it as a vector and program it in C or whatever. And that's great. However, you have an issue. If it's really slow, it's a lot worse than the greedy algorithm, which also can produce base P decompositions, but falls prone to floating point errors. So we want to make sure that this actually terminates fast if we want to use it that way, which we did a little bit. And so to prove it terminates fast, you take slow termination and you actually build a better hammer. And so this became two of the key techniques in our research, which is kind of, it feels almost circular. So you prove a really bad bound for termination, and then you're able to improve that bad bound because you know something. Namely, you look at the final state and you know that that final state has to be a base feed decomposition. And you can lift incredible results about what base feed decompositions look like from algebraic number theory. So there's papers in Fibonacci Quarterly about these decompositions, and you can look at those algebraic number theory results, interpret them in terms of the game, and that gives you actually a left bound on the final state. But then, because you know the future, and you basically know how splits and combines can affect the left bound, you can kind of build backwards and say, okay, I have this many combines, and I get a better left bound, and that better left bound then gives you fast termination. Fast termination is not the best because it depends on the length of the initial state. So how long your chain of summands is, which is good, but not the best you can do. You can do even better. And so what we were able to do is we were actually able to say, okay, we really want to say that this is like polynomial in the number of chips you start with, no matter how you arrange those chips. In fact, we're going to get O then squared. And the way we're able to do this is you look at the final state, and your chips have ended up distributed all over the place, and there's just ones hanging out. And what you're able to say is, oh, if I play the game backwards, only certain regions can interact. And because only these certain regions can interact, we can bound each of those regions independently. And each of those regions is only in the base phi like representation, and it only depends on that information, which is known at the start. And so you can go up, kind of follow this tower, and show that the termination only depended on the number of chips. It's actually very fast. And so, next slide. So these are our theorems, essentially. So there's a tight left bound of -2n minus log phi n on the leftmost used edge of a game that begins with n chips at the 0th index. So that negative log phi n, that's the algebraic number theory part about what a base phi decomposition looks like. And -2n is a combine at worst can move you 2n from the left bound, and you have at most n combines. And then another theorem that we have is that the longest Bergman game with n summands terminates in theta of n squared moves. And furthermore, an O of n game is achievable from any initial state, which is awesome. And so we had ideas for how to push this further. Namely, we can define what's called a positive linear recurrence sequence. And this was done for the Zekendorf game. And so this is a sequence which has characteristic polynomial given of this form. And I won't read all that out because it's kind of a pain. But the coefficients basically are non-increasing and all positive. And then this is an example of an is equal to n minus 1 minus 2 an minus 2 plus an minus 3. And then you can read out that sequence. So you can define the generalized Bergman game because the Bergman game is based on phi and its recurrence relation. And so you can also define games based on the roots of any non-increasing PLRS. And you call such games together the generalized Bergman game. And we were able to prove that the longest generalized Bergman game with n sum ands terminates in theta of n squared moves. And I want to actually point out something here. So if you could go back to the slide with the theorem about the Bergman game. So we have this furthermore statement here about an O of n game being achievable from any initial state, which is great if you're using this as an algorithm. It means it's linear. But if we go forward, we don't know that result for the generalized Bergman game. And that would be a great result to prove. I don't know the techniques that I would need to develop to be able to do it. And so that would allow us to produce base beta decompositions, which are widely studied in ergodic theory and algebraic number theory, using this algorithm for a wide class of bases beta. So then, just to finish up, we have some further questions about this game, both in the generalized case and in the Bergman game case. And so the first question is there a winning strategy for either player? So I told you for the Zekendorf game, it's known that the second player has a winning strategy. The proof is non-constructive, and we actually started out wondering if we could do a constructive proof. Turns out we couldn't. It's really difficult. And so that's the first question, right? And so because it was really difficult, we actually came up with a second question, which is given an initial state, there's an algorithm for determining the winner, right? It has to be because you could just play all possible games. And so how hard is it to determine the winner or the winning strategy on the Bergman game? And we were actually able to, in a separate paper, slightly extend the game onto graphs. And when we did that, we were able to show that this was a p-space complete problem, which means it is very, very difficult, harder than NP complete, like absolutely ridiculous. So it's conceivable that it's not even possible to determine the winner in the Bergman game, because if you slightly extend it, it becomes p-space complete. And then the other question is how far can we push those results about the Bergman game to these generalized Bergman game cases, which are a little bit harder and where we don't have quite as much power. Golden ratio turns out to be nice. Surprise for everyone. So there's some references and some acknowledgements for everybody. So we did this as part of the small RU. We were funded by the NSF grant. We had tons of co-researchers. This was one of our, at least my pet project, and I really love working on it, and a lot of people worked on it. And so we were also, of course, helped by Professor Stephen J. Miller, and he was an excellent mentor. Spent many days in his office talking about games, and at one point cogs, we had these little game states that we call cogs. So it was very fun. And now I think those are our references, and we're free to take questions whenever you'd like.
Thank you very much. Are there any